Hello AP Chem students and welcome to topic 9.10, cell potential under non-standard conditions. The learning objective for today is 9.10.a, explain the relationship between deviations from standard cell conditions and changes in the cell potential. So far we've been talking about electrochemistry calculations being at standard conditions, 1 to 25 degrees Celsius and 1 molar, but most involve non-standard conditions. So if we look here, this is the cell at standard conditions. And this is your half reactions that add up to give us the standard cell potential. So the cell potential is a driving force toward equilibrium. And the further the reaction is from equilibrium, the higher the value of the Ecell. But you can see here that here we have an Ecell of 110, and this is at standard conditions because we've got 1 molar and 1 molar. But if I deviate from standard conditions down here, where I have 1 molar still in my copper, but then I've diluted the zinc 100 times to give 0.01 molar, then my Ecell actually increases. You can see that. So it probably makes sense to you that the Ecell does not remain constant as electrical current is used from the cell. It changes when the concentration of reactants and products also change. So we can examine a Q versus K situation to show what happens when the conditions are more or less than 1 molar. So as a reminder, the reaction always tends to reach equilibrium, and therefore Q tends to become equal to K. And standard conditions, Q is equal to 1. And so you can see that on the graph down here. So what we're actually doing here is we're considering not only the fact that we're moving towards equilibrium, but also a deviation away from standard. That's what this topic is about. So if the reaction shifts towards the products, then the value of Q moves higher, causing the cell potential to decrease, meaning that the driving force on the electrons is also decreased. If the reaction tends towards the reactants, then the value of Q moves lower, causing the cell potential to increase, meaning that the driving force on the electrons is also increased, right? Because again, what we're trying to think about here is, are we moving closer to equilibrium or are we moving further away from equilibrium? Now, I know we just talked about Q versus K, but it's important to think about the fact here that we are actually not at equilibrium. So you are not going to use Le Chatelier's principle, because Le Chatelier's principle describes the response when a system at equilibrium undergoes a stress. Electrochemical cells that are at equilibrium have an Ecell value of 0, indicating that the cell is dead. Therefore, if you're starting with a working electrochemical cells, they're never at equilibrium. They're not at equilibrium until they're dead. So you're not going to use Le Chatelier's principle because we are not disrupting an equilibrium and seeing the response. We are talking about Q versus K and Q versus Q standard. But do not please call it Le Chatelier's principle. And so therefore we would not talk about a shift. We would talk about in which direction the reaction proceeds. So it proceeds more towards the products, it proceeds more towards the reactants, or it favors the products or it favors the reactants. Okay, so let's talk a little bit more about concentration cells. And you can see we're going to look at these images a couple of times. And so this is from a fantastic simulation from the American Association of Chemistry teachers. So far all the cells that we've been examining have generated potential difference by having different electrodes. However, this potential difference can also be created when the electrodes and half cells are the same. So you can see here, if you have the same solution and half cell, in both, you have the same reaction in both half cells and the same molarity, then the Ecell is 0 because you have no driving force. Everything is the same. We're at equilibrium here. However, if we change the concentrations to have different concentrations in the different half cells, then we call that a concentration cell. And it's a different way of applying the same idea of Q versus K. And so you can see here that we have different molarities. And so now we do have cell voltage. It is small, but it is there. Okay, and so this is an application of something called the Nernst equation. So the Nernst equation shows us how changing the concentration can impact the cell potential. It is on the equation sheet, as you can see down here. You will not have to perform calculations with the Nernst equation, but it's provided on the equation sheet to help you make qualitative deductions about the impact of changing concentration in electrochemical cell. So you can talk about how the Q value increases or the Q value decreases, and how that's going to impact your your Ecell relative to the E standard. And so we're going to look at that a little bit more. All right, so back to these pictures again. So in electrochemical cells that utilize the same half reaction for both cells, if the two half cells have the same concentration, then the cell is at equilibrium. The delta G value is 0 and the cell potential is 0. We already kind of talked about that. If the two half cells have different concentrations, then the cell is working to equalize concentrations in both half cells. The delta G value is negative and the cell potential is positive. Okay, so let's do this in a practice. So for the cell reaction here between aluminum and manganese, predict whether the E cell increases or decreases if the concentrations are changed to a concentration of aluminum of 2 molar and a concentration of manganese equal to 1 molar. So if you want to try this on your own, please go ahead and pause the video now. About to go through the answers. Okay, so here again is the Nernst equation that you can see on the equation sheet. And so we're just going to apply it to this situation. So let's first write our Q equation. So we have aluminum 3 plus in the numerator, and that is going to be squared because of the coefficient. And then remember, solids are not included. And then in our denominator, we're going to have manganese 2 plus, and that's going to be cubed. Again, solids are not included, so that's not going to appear in our Q expression. So then our new concentrations are 2 for aluminum and 1 for manganese. So the manganese actually stayed the same, but we doubled the aluminum, and then that is squared. That term is squared, and so our Q now has a value of 4. Before, our Q had a value of 1, our Q standard. So our Q is greater than Q standard. Therefore, the RT over NF natural log of Q term will be larger than it is at Q standard, meaning the E cell will decrease relative to E standard because we've subtracted here. So basically what we're saying is that we have proceeded more towards the products, which does make sense because we have 2 molar here. And therefore, our E cell has decreased because we are closer to equilibrium than we were under standard conditions. Okay, so then comparing side by side standard and non-standard conditions. So recognize that at standard conditions, half cells have the same reaction, the concentrations of solutions are equal, the cell is at equilibrium, and therefore the E cell is 0. Under non-standard conditions, the half cells still have the same half reaction, the concentrations of the solutions are different, the cell is working to equalize concentrations in the half cell, and therefore your E cell is not equal to 0. And you can see that up here. In this situation, it's 0.068. So let's talk about how you continue to produce voltage in concentration cells. So concentration cells will continue to produce voltage as long as the concentrations in the half cells are unequal. The direction of the flow of electrons will be as follows. So reduction will occur in the cell of higher concentration so as to lower the concentration of the ions in solution based on this half reaction. So you have a metal with some charge, and then it's going to be reduced. Remember, reduction is gain of electrons, and then it would form solid. So that would remove kind of the excess concentration, if you want to think about that, relative to standard. At the same time, remember the oxidation will occur in the cell of lower concentration so as to raise the concentration of ions in that solution. And so in that case, you have the opposite process. Oxidation is loss. And so then this would increase the concentration as the reaction proceeds. And therefore, the electrons will flow towards the cell of higher concentration. Recognize that the farther the cell is from equilibrium, the word from should be there, the greater the E cell will be. All right, so what should you be able to do with this? Well, you should be able to explain how a concentration cell works and understand why Le Chatelier's principle cannot be used to explain electrochemical systems. You should also be able to make comparisons of Q values to determine how changes in the cell as it progresses impacts the E relative to your E standard, and then apply the Nernst equation qualitatively to discuss the impact of concentration on cell potential. And that's it for today. This is our second to last topic in AP Chemistry, so we have one more video to go, and then we will be done with the course. So I'll see you soon for topic 9.11.